Good morning. Before starting the next main stream of land utilization for civil engineering practice, in continuation to the yesterday's port and harbor, there is one more dedicated harbor system, dock, dock or port and harbor system for oil extraction and natural gases. So it's a dedicated system. Yesterday we have seen the so many purpose of docks. In addition to that, a dedicated dock system should go to the deep sea too. Should be these port and harbor structures are almost near the shore, not going deep into the deep sea. But that has to go deep into the deep sea. Oils and natural gases such as petroleum products, petroleum oil, diesel, then the LPG, liquefied petroleum gas, and liquefied natural gas. So that is also one of the areas where these platforms and the container terminals to extract the oil, then processing will be our sister engineering fields will take care of. The transportation of this processed fuels, for which facility has to be provided similar to the other dock structures. So for container terminals, then highways and railways connectivities, there should be a small adjacent place where these processes can be conveniently done. So that is also one area of port and harbor structures. Now coming to the next mainstream of land utilization in civil engineering is that of agriculture and irrigation. Agriculture and irrigation. Irrigation engineering and irrigation structures or hydraulic structures, otherwise called hydraulic structures. The new terminology for this is water resources engineering. Water resources engineering is also, which includes the irrigation and the hydraulic structures. Agricultural engineering, this irrigation engineering and design of hydraulic structures, it's core subjects in civil engineering. Usually in the pre-final year or final year engineering students may have to undergo two subjects. One is the irrigation engineering, the other is the design of hydraulic structures. There will be electives in addition to these two core subjects. One is agricultural engineering. Agricultural engineering is an elective. It's not usually it will not be a core subject. Similarly, hydrology, hydrographs, hydrology, hydropower. Hydrology and hydrograph will be studied in irrigation, but in-depth knowledge of this, and there will be one elective. There was probably in the water resources stream, hydropower engineering. So hydropower engineering and agricultural engineering will be electives. So irrigation engineering is to cater the need of agriculture. They are interrelated very much. So it's also a long and large stretch of water courses. It's a process of supplying water to the agriculture. So large quantity, voluminous quantity of water is required. It has to be stored, it has to be collected, it has to be stored, it has to be distributed, and it has to reach the fields where agricultural operations are taking place. So irrigation is the process of scientifically supplying water to the agriculture according to the requirements of the crop to be cultivated on the land. That is known as the water requirements of crop. To meet the water requirements of crops, the stream of civil engineering, irrigation, takes care of it. Irrigation engineering. Natural rainfall will cater to a great extent the need of the agriculture. That is why agriculture operations are rain oriented, season oriented. Usually, if you take paddy, which is the main agricultural product, there will be two crops. In India, it is called as Kharif and Rabi. Kharif, Rabi, Kharif and Rabi crops. There may be perennial crops such as sugarcane. Sugarcane is an annual perennial crops. Cotton. So perennial crops annually you require throughout the year the water. For paddy you require water for 6 months, again a gap, again you require. During the 6 months, crop period may be around 3 or 4 months. So 2 months vacation they will get. That may not be in the case of perennial crops. Irrigation has to cater any type of crop according to its requirement of water. The area which is irrigated by an irrigation system, a scientific irrigation system, is known as an arid region, ARID, arid region. Usually regions are semi-arid. Some part will be supported by rain, the other part will be supplemented by irrigation. Both rain helps and the irrigation system helps. So farmers know the season according to the availability of rain, when the rain will come, when the seeds have to be sown or transplanted, by which they will get maximum water from rain as a source. But now the nature itself has shifted its duties. As you have the global warming and the climate change, prediction of rainfall may be accurate, but the rainfall frequency and the season when you have rain and you don't have rain, that gets staggered, it gets shifted. There is a categorical shift from the conventional seasons. That poses a problem and challenge for the farmers. So at this context, the role of irrigation in meeting the requirement of the crops for water is more significant and relevant. There are two types of irrigation systems. One is called the storage irrigation system. Another is called the direct irrigation system. Storage irrigation system is otherwise called tank irrigation system. Tank irrigation system. and the other is called direct irrigation system. So supply, according to the type of supply of water to the agricultural lands, two types of irrigation systems. One is tank irrigation, other is direct irrigation. Tank irrigation means you have a storage basin, a tank, huge tank in which you will store water. That water from a main tank, it may go to the sub tanks. From the sub tanks, it will be fed to the agricultural land. Tank irrigation is a direct supply of water to the agricultural land, but it is not called direct system. Tank irrigation means storage irrigation, or tank irrigation means store water. The source is rainfall. You store water when peak rainfall are there, keep it and use it when the crops require water. Means directly irrigating into the agricultural fields. That is tank irrigation. The direct irrigation system, you have network of distributors known as canals. In a direct irrigation system, you have a network from the storage, from the water reservoir. You will have a dam. When you have a dam, that dam will be pounding water on its upstream side according to the catchment. Catchment is the area, drainage area from where you get maximum water that will be kept at the upstream of the dam, which is known as the storage reservoir. This water will be utilized for electric power. It may be utilized for navigation. It may be used for fish culture. It may be used for boating. At the same time, it will be used for irrigation too. Then that reservoir is called multi-purpose reservoir. It does multi-purpose, for which you have to store more water. The dam will be large in size, in its height and width. So irrigation will be definitely one of the purposes. From the dam itself, you treat the water and use it for domestic water supply also. Treated water from the reservoir. So water supply also is one of the functions of a reservoir, for impounded water by construction of a dam. So from the dam, dam has two sides. One is the upstream side and the downstream side. That's the technical names of the two sides. The front of the dam, if you see from front, it's called the downstream. The rear of the dam is called the upstream. The upstream water is stored, then you have the dam, and when you open the shutters, water will come and fall. Usually you would have seen spillways. This is because the falling water will have a lot of energy. So it will come and fall with great impact. So we have to reduce this impact force. So we will have a pool of water known as cistern or stilling basins. From the height of the dam, when water comes, it will gradually enter a water cushion. Already there will be a water cushion, a wider and broader basin with baffled blocks, staggered baffled blocks. So when water comes with a greater velocity,
fundamental objectives of modern infrastructure, from flooding rivers to irrigation canals, stormwater drainage facilities to aqueducts, and even the spillways of dams. So engineers need to be able to predict how water will behave in order to design structures that manage or control it. And fluids don't always behave the way you'd expect. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about one of the most interesting phenomena in open channel flow, the hydraulic jump. This video is sponsored by NordVPN. Feel safe online, anywhere, anytime. More on that later. Fluid dynamics might sound as complicated as rocket science, but unlike rockets, you probably already have some intuitions about how water flows. The study of how water with a free surface behaves, that is, not confined within a pipe, is known as open channel hydraulics. This field is especially useful in civil engineering, where structures can't usually be tested at scale. We can't build a dam, cause a flood to see how well the spillway works, and then rebuild it if the performance isn't up to standards. Instead, engineers need to be able to predict how well hydraulic structures will perform before they're ever constructed. This is the definition of engineering, to take theoretical knowledge of science and physics, in this case fluid dynamics, and apply that information to make decisions about the real world. One of the most important parameters in fluid dynamics is velocity, or how quickly the water flows. Sometimes velocity is a good thing, like when you're trying to move a lot of water quickly, for example in a flood. Sometimes velocity is a bad thing, like if you're trying to avoid erosion. Either way, it's almost always a key criterion when designing hydraulic structures. But the velocity of flow isn't the only velocity that's important in fluid dynamics. We also care about the velocity of waves, or how quickly pressure disturbances in a fluid can travel. If the flow velocity is exactly equal to the wave speed, we call the flow critical. But it's more likely that these two velocities are different. Slow, tranquil flow conditions are called subcritical. In this case, the wave speed is faster than the flow velocity. You can see that the waves can travel against the flow direction. Because of this, the depth is controlled by downstream conditions. You can see that anything I do upstream isn't changing the depth of this flow. Fast-moving flow is called supercritical. In this case, the flow velocity is faster than the wave speed. You can see that the waves aren't able to propagate upstream. Supercritical flow is controlled on the upstream side, so nothing I do downstream affects the depth of the supercritical flow above. A flow profile can naturally transition from subcritical to supercritical, that is, from slow to fast. For example, if a channel changes to a steeper slope or a cliff, many types of flow measurement devices rely on forcing a flow to transition from sub to supercritical because there will be a unique relationship between the flow rate and the depth for a given geometry. Maybe we'll talk more about flow measurement in a future video. But when flow transitions the other direction, when a fast-moving supercritical flow transitions to a more tranquil subcritical condition, something much more interesting happens: a hydraulic jump. The classic demonstration of a hydraulic jump can be seen at the bottom of your sink. Open the faucet and watch how the flow behaves. You can see the fast-moving flow right as the stream hits the sink, and the abrupt transition of the hydraulic jump to a slower-moving flow. But the sink demo isn't the best example because it happens due to surface tension, not gravity. Plus, it's kind of boring. So I built this flume in my garage to give you a better look at the hydraulics. If I open the upstream gate by just a little bit, I can create supercritical flow in the flume. Now, if I obstruct the area downstream, I can force the flow to transition into subcritical. Right where the flow transitions, you can clearly see the hydraulic jump. This phenomenon happens naturally in certain locations. Steep mountain streams often have supercritical flow, crashing into rocks and changing slopes, creating whitewater and turbulence, and the occasional hydraulic jump. Also, a tidal bore occurs when an incoming tide forms a wave that travels upstream against a river. These events only occur in a few places across the world, but it's fascinating if you get to see it in person. In many cases, the bore travels as a moving hydraulic jump, similar to what you see here in my flume. But jumps aren't just natural phenomena, they're important in hydraulic structures as well, especially for energy dissipation. A major part of the job of a civil engineer working in the field of hydraulics is designing against erosion from the flow of water. When we try to control the flow of water, that often leads to the potential of having fast-moving, erosive conditions. For example, when we put water in a culvert rather than allowing it to flow over a roadway, it can pick up speed in the pipe. When we line a ditch or creek with concrete, the smoothness speeds up the flow compared to natural conditions. And when we make releases from a reservoir behind a dam into a spillway, the water can come roaring down at extremely high velocities. This supercritical flow can cause erosion and eventually lead to failure of the structure. So most hydraulic structures will be equipped with some form of energy dissipator on the downstream end to reduce the velocity of flow and protect against erosion. There are all kinds of hydraulic energy dissipators, but for large structures like spillways, the most common types rely on the formation of a hydraulic jump. Because a hydraulic jump causes so much turbulence, it's able to effectively dissipate hydraulic energy as heat. So many energy dissipators, also called stilling basins, are designed to force a hydraulic jump to occur. There are many types of stilling basins, but most use different combinations of blocks, insills, and overall geometry to control how the hydraulic jump forms. The turbulence stays within the stilling basin with the objective of having smooth, tranquil, subcritical flow leaving downstream, minimizing the potential for erosion which would otherwise threaten the integrity of the structure. Hydraulic jumps don't just serve utilitarian purposes. Recreational whitewater courses can be found across the world, and many of these courses make use of hydraulic jumps as artificial rapids. In fact, many kayak parks started out as obsolete dams in need of removal, a perfect opportunity for replacement with something more beneficial to the community and the environment. Freestyle kayaking, also known as play boating, involves performing tricks in a single spot. Play boaters use natural and artificial hydraulic jumps to stay in one spot. I've never tried this myself, but it looks like a lot of fun. Next time you see water flowing in an open channel, try to identify if it's sub or supercritical, and keep your eye out for hydraulic jumps.
Water comes from a height, it will not go like this. If you come like this, then again it will rise up. That is known as the hydraulic jump. This hydraulic jump automatically dissipates the energy to a great extent. Then the water cushion, then the baffles box. So once this water comes here, then it goes to the river. The river. So first component of a direct irrigation system is the river. From the river, there will be budding out of canals. Budding out of the canals. One on the bank canals, main bank canals. So the river will have a left side and a right side. If the main canal is at the left side of the river, it is called left bank canal. If the river is at the right bank of the canal, it is called right bank canal. Bank means embankment. From the word embankment, because it is a soil structure. So from the word embankment, that bank has come. So left bank canal, the right bank canal. They are the main canals. So water from the river goes to the main canals. We will see tomorrow how the network gets extended. Thank you. God bless.